Yeah, so we're on 2.7 finishing up here. Um, let me just explain what all those words mean. On example 10, it says to find that. So if you saw that, what would that mean to you? This is the second derivative of y with respect to x, right? And we're going to have to do it implicitly. So remember, we have to use implicit differentiation, first of all, when the equation that we're differentiating, what? Can't be solved for y, or we're too lazy to solve for y, right? Because it works every time. So even though we can't solve for y, notice that all the problems that we've worked so far, once we've taken the derivative, we have been able to solve for dy dx, yes? Because the derivative will be a linear function of dy dx in terms of the other variables. So even though you can't solve for y originally, you can solve for dy dx. So whenever you're going to be taking the second derivative, it's best to go ahead and solve for dy dx, like we've been doing, and then proceed to the second derivative. It's going to make the algebra a whole lot easier. And that's what all this stuff says. Now, this is another thing that you want to read carefully. It says find the second derivative of y with respect to x as a function of just x and y. That means in the end you can have numbers, you can have plus or minus signs, but you can't have any variables other than x and y. So, let's set out. We have this right here. Can you solve it for y as a single equation as a function of x? No. Because it's y squared, you're going to have to go plus or minus. Do y'all know what the graph of that would look like? Going back to your Algebra 2 days? What? Not quite an ellipse. Good. Oh, actually, that's x cubed. If that were x squared, not x cubed, it would be kind of elliptic, but because one of them would be negative, it would actually be a hyperbola. But that's actually x cubed, so that's not even going to be a conic section. So if we can't solve it for y and we need dy dx, not a problem, right? What do we show first? D dx to both sides. Good. And we got a check for that on the quiz. Now, how could you not earn that check? Here's what I see some people do. They put dy dx on both sides. And, of course, that's no longer a verb. That's a noun. That becomes not take the derivative of what follows. That's rather multiply dy dx times that, and then your next step would be to distribute it in. So very, very different meaning. All right, so here we go. On the left side, we get 6x squared dx dx, which we don't need, minus 6y to the first times dy dx, which we do need. And on the right side, we get 0. Now, let's look at this line right here, because I want to come back to it. And I'm going to show you, first of all, what it looks like if we don't solve for dy dx. If you know you need the second derivative, you know what you could do? You could take the derivative of both sides with respect to x again. Is that legal? It's very legal, right? As long as you do it to both sides. Since I needed the second derivative, let's go ahead and do that. Let's see what we end up with. Derivative of 6x squared is 12x. Now notice what I have to use in the second term. That is now 6y times dy dx. That's going to be the what rule? Product rule. So the derivative of negative 6y with respect to x is negative 6 dy dx times the dy dx that's already there, goes along for the ride, and then minus 6y times the derivative of dy dx. What do you think the derivative of the derivative is? The derivative of the first derivative is the second derivative. So if that were y prime, we would call it y double prime, but in Leibniz notation, we use d squared y over dx squared. So the first one in the first term that's in green, that's dy dx times dy dx. That's the derivative times the derivative. In the second term, that is the second derivative. And then on the right side, of course, what's the derivative of 0? 0. Now, all we have to do is solve for dy dx, right? Let's do that. I'm going to bring the terms across. So that's going to be negative 6y times the second derivative of y with respect to x. And when I bring the other terms across, I get positive 6 times dy dx times dy dx is dy dx squared. And then I have a minus 12x. Now from here, all I have to do is divide through. And I get 6 times dy dx quantity squared minus 12x all over negative 6y. And then, of course, we could clean that up a little bit. But if we were doing this on a free response, don't forget to square the x in the bottom on the derivative, second derivative, you wouldn't necessarily have to divide out common factors. But could you stop right there? No. And this is where some students kind of do all this work and then not get full credit, because it asks you to find it as a function of what? X and y. And notice right here we have the second derivative explicitly solved for. That's great. But it's in terms of x and y and dy dx. So what you have to do now is somehow get rid of the dy dx and substitute it with something that it's equivalent to that's in terms of x and y. Crap. Did we ever solve that for dy dx up above? Yeah, we could do that. Let's do that. Let's keep going. You're still going to have to solve for dy dx, but if you factor out a negative 6 from the top, let's do that. If you factor out a negative 6 from the top, I'm going to call it positive 2x minus dy dx squared. I'm going to flip the terms. That gives us a negative 12x and a positive 6 all over negative 6 times y. Sure, yeah, we could do that. And that would be something that I would hope you would do. So a nice cleaned up version of the second derivative is now just 2x minus the first derivative squared all over y. So that looks a lot prettier, but it's still not going to be full credit because now it's in terms of dy dx and x and y. So what I need to do then is I need to somehow solve for dy dx and replace it in there. So let's retreat back up here to this line. And this is why I copied and pasted it. Or copied it, now I pasted it. If I need to plug that in down here, all I got to do is solve this for dy dx, yeah? Let's do that. I'm going to get 6x squared equals positive 6y dy dx, bringing it over to the right just because I eschew negatives. Everyone okay with that? And now when I divide through by dy dx, I'm going to get 6x squared over 6y, which is, the 6's will divide out, right, to give you x squared over y. Now I can substitute that, x squared over y, way back down here, and I get my final cleaned up version of the second derivative. It's 2x minus x squared over y, quantity squared all over y. Now, technically, is that the second derivative in terms of x and y? Yeah, so you could stop there. Let's keep going, because another way I could ask this question is I could say, show that the second derivative equals, and I can give you the answer that's nice and cleaned up, and now it wouldn't be that. So let's keep going here. If I square the quantity, I get x to the fourth over y squared, all over y, and that's a complex fraction. So you can either stay, change, flip, and distribute, or do what we've been doing all along, multiply by LCM over LCM. Maybe keeping that over 1. It's a nice way to kind of clean that up. And from there, we should end up with a nice version of the second derivative. If I distribute now, I'll get 2x y squared minus, your y squareds divide out in the second term, right? See that? Leaving just an x to the fourth all over a y cubed. And that is about the prettiest version of the second derivative we're going to get. Now, notice that I had to come back up here anyway after I took the first derivative. I had to eventually come back and solve it for dy dx. That's what all this verbiage up here is saying. When it's an implicit equation and you have to find the second derivative, it's probably best to find the first derivative and then solve for dy dx to get that. And then take the second derivative. So what I did from here, from this line on, is what I would not recommend that you do. It'll absolutely work, and it was good practice on implicit differentiation, but don't do it that way. Okay, take the first derivative implicitly, solve for dy dx like we've been doing, and now let's go ahead and take the derivative with respect to x of both sides. Not that you would need to show this step here, because now it's explicitly solved for dy dx, but it does a nice job of indicating our method. You could, and then use the product rule. I'm going to use the Hody-High rule, but you're welcome to use the, bring it to the top and use the product rule with the chain rule. That's fine. Now, look at the left side. What's the derivative with respect to x of dy dx? D squared y over dx squared. And I showed you earlier that that's kind of how that notation works. There's two d's in the top and two dx's in the bottom. We just don't put parentheses. And over here, I'm going to use the quotient rule. So ho, d high is 2x minus high. What's d ho? The derivative of y is 1 times the chain rule dy dx all over ho ho, which is y squared. Now that is nice because it was a lot easier to do. Notice this this line here. There was a lot more going on than there was right here. It's already solved for the second derivative. That's nice too. But once again, we can't stop because it's not in terms of x and y. Now, how do we get rid of the dy dx? We substitute it back in. But you know what? We already have it. We don't have to like go out and do extra work. We just use what we started with. So it's going to be a lot easier, less likely to make careless mistakes. I'll reshuffle the factors in the first term, 2xy minus x squared times x squared over y, and then all over y squared. You could technically stop there if it said as a function of x and y, because we did that. But again, if you're trying to match it up to a multiple choice answer or something, that would not be it. So if we multiply by y over y now, because that's your miniature denominator, we get 2xy squared when we distribute to the top. And then your y's divide out, leaving minus x squared times x squared, which is x to the fourth all over y cubed. Is that what we ended up with down here? Yeah, same thing. Pretty sweet. Which way was easier? Second way, yeah. And if you do it the first way, that's fine if you like the extra practice. But remember, you're going to have to go back and solve for dy dx anyway. So you might as well do it first, and then it makes that second iteration a lot nicer. Again, so implicit differentiation, we use it when we can't solve for y, or we don't see that it can be solved for y, or we're too lazy to solve for y. But the derivative, its derivative, will always be solvable for dy dx. It's going to be a linear function of dy dx in terms of the other variables. Okay. Any questions on implicit differentiation? Kind of fun, right? We're going to learn the derivative of several other types of functions later on in the year, and we're going to learn one more derivative technique. This would be like a derivative technique. But we're getting close to the end of our derivative technique, so we're kind of to the point now where we just start using them to answer bigger and better questions. All right, that's it. We're done. Worksheet is due tomorrow. We'll probably save a quiz until a couple days from now since we just quizzed today.